What's up, everybody? Hope you're having a great day. We're going to react to the asteroid assault, the most recent, the NASA probe that slammed into the asteroid. So if you're new here, I'm a mechanical engineer myself. Been working in the industry for, out of school at least, almost 2 years. I graduated in 2021. Just want to hang out with everybody and look at some really cool stuff. So before we get started, if you could like and subscribe, that would really help me out and I would appreciate it greatly. So let's get right into it.
Craft the size of a refrigerator.
I think I had audio off there for a second.
On the 26th of September 2022, a 570 kilogram spacecraft the size of a refrigerator rammed into an asteroid at 6 kilometers per second, launched aboard the fossil-fueled powered Falcon 9.
6 kilometers a second. Let's see what kind of speeds we're looking at here. 6 kilometers per second. That's pretty freaking quick. 13,000 miles per hour. Pretty good.
Dinosaurs finally clapped back. 66 million years after the asteroid that ended the dinosaurs, an unsuspecting asteroid was struck with an impact equivalent of 3 tons of TNT, and we caught it all on film. This mission is perhaps the most important experiment NASA has ever performed. Data and information that could one day save us from the same fate as the dinosaurs.
SpaceX.
The asteroid we struck, Dimorphos, is 160 meters in diameter, much smaller than the 10-kilometer wide asteroid that exterminated the dinosaurs all those years ago, but large enough to unleash over 300 megatons of energy if it collided with Earth. 6 times more powerful than the most powerful nuclear weapon ever used. In the weeks since, scientists have been studying the results, calculating how effective our first asteroid redirection test was. However, the work that went into this mission far extends the last month of scientific study. For years, scientists and engineers carefully planned which asteroid to hit, how to hit it, and how to confidently and quickly measure the effect of the collision. To understand the achievement of the DART mission, let's dive into the engineering and physics of its planet defense mission.
Yeah, that was a cool transition.
The DART spacecraft itself hosted no scientific instruments, designed to be a low-cost spacecraft with just the tools it needed to complete its mission.
Real quick before get too far into this, one really cool kind of audio documentary that I've listened to is called 13 Minutes to the Moon. It's by the BBC. It's on Spotify. It might be on some other platforms as well, but it really put into perspective how to navigate into space, and especially the Apollo 13 mission that barely made it back, that had an explosion in one of their oxygen tanks. Just thought it was really well done, all the details, and just being able to relive the history of that. So I wonder how much of that is going to kind of show up in here as far as like navigation and stuff like that in space.
Cameras to spot its target, star trackers to navigate through space, a propulsion system to direct it toward its target, antenna systems to speak with Earth, and an onboard computer, whose software has its roots in military missile technologies.
Javelin.
However, DART did release a small Italian-made spacecraft designed to record the collision, giving us this footage showing a massive plume of debris being ejected from the asteroid on impact. The Falcon 9 rocket did the majority of the work in directing DART toward its target, Dimorphos. This was a unique target, chosen for a very important reason. It's a moonlet, a tiny moon orbiting the larger asteroid, Didymos. DART's camera gave us a glimpse of Didymos as it sailed by at a breakneck speed, closing down the remaining 920 kilometers in just 2.5 minutes. It computed and adjusted its trajectory using hydrazine thrusters, guiding the spacecraft to a head-on impact with the moonlet.
Hydrazine.
In these final moments, DART shut down its thrusters, allowing the camera to take clear images of its impending doom, and giving us a clear picture of the rock we just obliterated 11 million kilometers away. So, why this rock in particular? There are countless
Isn't that crazy? We just sent something up with a rocket and we just hit a rock in space 11 million kilometers away. Isn't that crazy? Physics, man.
asteroids orbiting the Sun. However, in order to study the results of impact, we need a specific kind of asteroid. First, Dimorphos was passing close to Earth, passing by at 11 million kilometers at the time of impact.
Pretty close.
We have tracked Dimorphos and have confident predictions of where the asteroid is going to be at any given point in time. This allowed us to choose an optimal window for collision. Our model showed that on October 4th, 2022, the asteroid would be at its closest approach for the next 40 years.
Oh, within the next 40 years. Okay, that makes sense. It's kind of like the alignment of basically launch schedules for rockets. There's certain windows that you have, whether it's weather or otherwise, where you are spin-wise in the Earth. I don't fully understand all that completely, but I'm at least aware of it. So kind of cool how all those things get taken into account. Wow, 40 years. They're able to predict 40 years into the future. That's pretty consistent then. Interesting.
The next time it would be this close to Earth would be 2062. This was the perfect opportunity. However, we struck it a week early because the asteroid would be at its brightest to us at its closest approach, allowing us to better observe the results of the collision. This is the next reason this asteroid was chosen. The goal of the double asteroid redirection test was to redirect an asteroid with just enough force to change its trajectory by a marginal amount, enough to avoid a collision with Earth. A change of just 1% could be enough to avoid a catastrophe. But here lies the dilemma for scientists. How do we measure such a small change in trajectory of an object 11 million kilometers away?
So they actually tried to move the asteroid. I did not know that. I thought they were just ramming it in there for scientific measurements, or I didn't know they were trying to knock it out of orbit slightly. Wow, interesting.
Even the footage from a spacecraft near the collision is not much to go off. Confidently measuring an impact with an asteroid orbiting the Sun would take years, as we'd need to measure multiple orbits to assess the differences before and after the impact. Instead, scientists turned to binary systems for answers. There are systems of asteroids where one smaller moonlet orbits a larger asteroid. All we need to know is that we changed the velocity of a moving rock in space. It doesn't matter if it's orbiting the Sun or orbiting another rock. However, not any binary system would make this experiment feasible. It is essential that we can measure the effectiveness of the crash from Earth. For this, the orbiting moonlet should have an eclipsing path, meaning that viewed from Earth, it would pass in front of and behind the asteroid during its orbit. The light reflecting from these two asteroids that we see here on Earth appears as a single point of light, and each time Dimorphos passes in front of Didymos, that light dims. Using sensitive Earth-based telescopes, we have timed these patterns to measure the orbit of Dimorphos at 11 hours, 55 minutes. Using these same techniques, we can measure the change in orbit. Dimorphos is only visible from the southern hemisphere, so NASA reserved time on telescopes located in Chile, South Africa, Australia, and New Zealand. Joining the Earth-based telescopes, Webb and Hubble were also used to image the asteroids at the time of impact. Of course, to achieve all this, we first needed to hit the asteroid. That was no easy feat.
Lots of math. If you're in college right now for any kind of engineering, whether it's mechanical or electrical, yada, 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 just trust me, the math will be worth it someday. No, you're not going to use derivatives all day in your day job, but it will pay off in the end. It's more of how to think and problem solve is the biggest thing. And this is someone who's not very good in school. I just above a 3.2 GPA, and that's with a lot of help. I am not a great student. I'm a lot better with my hands and stuff. But if you're struggling right now, just know that it will be worth it. Just get through it, and you'll be there, and it'll be worth it. Sorry, get off my soapbox.
Asteroid was too far away to manually direct the spacecraft. There would be a lag of 1.5 minutes. At 6 kilometers per second, a lag this large would have the spacecraft travel over 540 kilometers.
So this is probably going to be extremely similar to how the Mars rover, how they dropped it off with kind of that jet helicopter in a way. It's all automated, just because of the lag time. So see what they say here.
Before receiving instructions. When trying to hit a target only 160 meters in diameter, lags like this required an autonomous navigation system. The spacecraft was loaded with a camera attached to a small 20 centimeter wide telescope, and circuitry no more powerful than that of a PlayStation 1. Every second, it would take a picture and calculate the thrust needed to stay on course, working very similarly to visual guidance software used in military applications like the Javelin missile. DART used 12 directional thrusters to hit the small dim moonlet. DART was also equipped with the next generation of ion thrusters, NEXT-C, which is 3 times more powerful than NASA's previous generation ion thruster, NSTAR. Ion thrusters are highly efficient, accelerating heavy ions of xenon to extreme speeds of 40 kilometers per second using an electromagnetic field, 10 times faster than a traditional rocket engine.
So we're just moving atoms with electricity, and law of conservation of mass and Newton's law of, equal and opposite reactions. It just goes back to the simple basics. It's crazy how they can, those ion thrusters are really interesting. I've seen some YouTubers make he made like almost a wind tunnel. I forget that the name of the YouTuber is. I'll put that in the video later, but he did like a wind tunnel, and it looks like a bunch of kind of almost fishing string, and he had some layers of it, and he did a bunch of different cool tests and configurations of it. And heck, I almost want to build one. It's not too difficult, I don't think. Just need a power supply and a bunch of wire and the framing, but yeah, that's a really cool technology. It's interesting.
These ion thrusters were powered by new, specially developed lightweight solar cells that deploy from a roll, called a Roll-Out Solar Array, or ROSA. This solar array was successfully tested on the ISS in 2017, although in a strangely hilarious video, the arrays were gently ejected from the ISS because there was a fault in retracting them at the end of the test. Part of the solar array was also used to demonstrate a new solar collector technology that would concentrate sunlight on high-efficiency panels, increasing their power deep in our solar system, where solar radiation rapidly drops off thanks to the inverse square law. A technology that would be extremely useful for powering an ion thruster, allowing us to reach asteroids further from Earth and giving us a better chance of changing their trajectory early. These systems were successfully tested on DART. However, Ed Reynolds, the DART program manager at APL, revealed in a post-impact briefing that the NEXT-C thruster was actually only tested for a short 2-hour period during flight. An unexpected issue arose that could have caused 100 amps of current to run through the thruster, which it had not been tested to withstand, forcing the team to make a decision to not continue testing the thruster, instead relying completely on the hydrazine thrusters to focus on the primary asteroid redirect mission. And while this is disappointing, finding a new issue is an important part of the testing process, and it didn't impact the mission at all. The mission itself was a massive success. After just 2 weeks of gathering...
That's one thing too, that it just takes time when you get out of college and into your engineering job. If you do any kind of product design or anything like that, which is primarily what I do on stuff for the military, is test. You can make it look pretty in SolidWorks all you want and have some cool stuff on paper and maybe a simulation. But have you actually tested it? Have you actually fit it? Have you printed it? Or have you 3D printed it, assembled it, put it in an environmental, there's a whole host of characteristics, and there's going to be, managers and project engineers and other people that are going to be poking holes in your design, and you got to make sure that it's watertight. And so that's just a word of advice to anybody who's kind of going through college and, wondering maybe what it's like in the field, so to speak, with an engineering job. And it's not a quick process a lot of the times. And that's one thing I struggle with, is I want to, I got this idea, I want to get it going. And then I usually overlook something. And a lot of people ask a lot of good questions, and they're just there to help. So it may seem like they're criticizing your work, but it's really just for the betterment of the idea. And so testing is essential. So if you're ever in that position, you're a young engineer, test as much as you can, 3D print as much as you can to get stuff in your hands and to physically assemble and put stuff together. That's going to put you way ahead of the curve of a lot of people. And it'd be smart to learn how to use a 3D printer too. Just a tip.
Gathering data, NASA announced on October 10th the effects of the collision. Striking only 17 meters from the asteroid's center, DART practically struck the bullseye.
That's pretty good.
Not just changing its orbit by 1%, but by a relatively massive 4.5%.
Wow.
Reducing its orbit around Didymos by 32 whole minutes, down from 11 hours 55 minutes to 11 hours 23 minutes. This is a mission minutes to 11 hours 23 minutes.
Wow.
This is a mission
pretty crazy.
Worth celebrating. We are now confident we can deflect an asteroid like Dimorphos if the need arises. Beyond moon missions, beyond Mars missions, beyond all the understanding NASA and other space agencies provide us, this mission has clear, understandable importance. We now have data and tools in our arsenal to protect our planet. We are now a little safer on this little rock floating through the vast, mysterious expanse of space. This mission was primarily designed to gather data on how a collision like this would affect the orbit of an asteroid. There were many questions to be answered about the geological composition of the asteroid and how that would affect the transfer of momentum from DART to Dimorphos, especially as most asteroids of this size are simply piles of rubble that have coalesced due to gravity over time and aren't a single solid mass, making exact predictions on the collision physics and how the orbit would be affected very difficult. Basic calculations of gravitational physics are pretty easy to learn, however, and understanding them gives you all sorts of fun powers, unlocking the knowledge of space travel and planetary motion. You can learn more about that by taking this course on Brilliant.
So, kind of back to what he was talking about with, the purpose of this mission. So that's a lot of what you do in at least in mechanical engineering as well. You have, maybe a design to obviously solve a problem, and you need to be able to build hardware. In most cases, build hardware and that you think will help solve that problem, and then you need a way to quantify that, a way to measure it, a way to observe it, whether that's through video, slow-mo video, whether that's through measurements. So these are all things that you got to think about when you're making things. Sometimes, you can just throw stuff in there and try it sometimes, but you also have to take a bit of a methodical approach and take your time and be able to measure things. So that's going to be, you're going to be able to, and let me back up a little bit. And the reason why it's also a good thing is when you go to your review meeting with other engineers and your boss and management and yada, yada, yada for this design review, you got to bring your receipts, right? You got to bring your test data, even if it did not do exactly what if it failed, let's say, it's still a good test because you got data and you learned from it. So always save everything you've done, write it down, get an engineering notebook, put your name in it, write stuff down, sign it, take lots of video, data, pictures, document as much as you can, because that'll come back more often than not to help you and not hurt you. So, just a little word of wisdom in just my first year and a half or so here in kind of the real world, so to speak. So, pretty cool video. A lot of stuff that I don't understand, even with space. I don't understand any of that really, how the orbit stuff works. I mean, the basics with gravity and velocity and your centripetal acceleration and everything. That makes sense, but how to navigate and all that's just kind of beyond me. But it can't be too difficult. Just a lot of math and a lot of people who are really smart. You could probably learn it. So I really enjoyed this video. Hope you guys did too. If you liked the video, be sure to drop a like down below, and give me a subscribe if you feel like you want to tag along for more videos. Thanks. Have a good day.